who do not know me, my name is Erica Copeland, and today we're going to be talking about the limiting reactant, the theoretical yield, and the percent yield. So before we move on to do some examples, let's first go ahead and go over the definition of the limiting reactant. The limiting reactant is the reactant that is consumed first and therefore limits the amount of product that is produced in a reaction. So with that said, let's go ahead and go to the board and do some examples. Alright guys, so I've written this reaction on the board where we have 2 slices of bread reacting with 1 jar of peanut butter and 1 jar of jelly to generate or produce 1 peanut butter jelly sandwich. And looking at this reaction, I ask you, which one is the limiting reactant? Think about it for a second. If you said 2 slices of bread, you are correct. It does not matter that we have 1 jar of peanut butter. It does not matter that we have 1 jar of jelly, because at the end of the day, when we run out of slices of bread, we're not going to be able to produce any more sandwiches. So when we run out of this reactant, we are no longer going to be able to produce any more product. Therefore, since this is what's going to be consumed first, is what's going to be limiting the amount of product, in this example, peanut butter jelly sandwiches, that we're able to make. Let's go ahead and do an example. So I've written this chemical equation on the board where we have 69.7 grams of silver nitrate reacting with 73.0 grams of potassium iodide in order to produce silver iodide and potassium nitrate. Our product of interest is going to be silver iodide. So with that said and this information on the board, I ask, which of these 2 reactants is going to be your limiting reactant? Well, the very first thing that you want to do is to make sure that the chemical equation is balanced. This one that we have on the board is already balanced, so we don't have to worry about that, but make sure that you keep that in mind for the future. So, if I want to know which of these 2 reactants is going to be my limiting reactant, essentially what I'm being asked is which of these 2 reactants is going to run out first or be consumed first. Or another way to think about this is which of these 2 reactants is going to be generating the least amount of product. Because if you generate the least amount of product, it means that you're getting used up first. So if that is the case, we're going to be going from 1 reactant at a time and figuring out which reactant is going to produce the least amount of product. And if we're going from 1 compound and finishing out with another compound, know that you have to go through the mole ratio. I'll say that again. If you're starting out with 1 compound and you have to finish up with another compound, know that you have to go through the mole ratio. So essentially what we're going to be going is going from reactant A, grams of A, to moles of A, and then you're going to be using the mole ratio in order to be able to cross out 1 compound and come out with a new compound. Moles of B, and then from moles of B, you can go to grams of B. However, in this example, if we're starting out with 1 reactant and we're trying to figure out how many or how much product is being produced, we don't really have to go all the way to grams. You can go ahead and just stop at moles over here, because if you generate the least amount of moles of a product, then you're also going to be generating the least amount of grams of a product. So I have over here the grams that I'm starting out with for each of the reactants. And we said before that we're trying to go from grams of 1 reactant to the moles of the reactant, to then use the mole ratio between the reactant and the product so that I can cross out the reactant and come out with the moles of the product. So with that said, we have grams over here of silver nitrate, and we're trying to go from grams to moles. And to go from grams to moles, we have to use the molar mass. So the molar mass for silver nitrate is going to be 169.87 grams over mole. And this is the same thing as this. Okay? So, if I'm trying to go from grams to moles, I'm going to write my destination, so what I want to end up with, on the top of the fraction. So moles is going to go on the top, and grams is going to go at the bottom. And looking at our molar mass over here, what you can see is that the moles are on the top and the grams are on the bottom, as opposed to over here, grams over mole. So all that we will have to do is to flip this fraction. So if we do that, then we have 169.87 at the bottom. Then you're going to go ahead and plug that into your calculator, and that's going to equal to 0.410314 moles of silver nitrate. Then we're going to be doing the exact same thing with our potassium iodide. We're going to go from grams to moles. So then again, what I want, which is moles, is going to go on the top, and what I want to cross out is going to go at the bottom. I want to cross out grams. So the molar mass is going to be 166.00. If you do this, you plug this into your calculator, and the answer is 0.439759 moles of potassium iodide. And just having a closer look, right, we've crossed out the grams, moles are our result, same thing here, we cross out the grams, and moles are our result. So you might be tempted to stop right here and say, ha, I have less moles of silver nitrate than moles of potassium iodide, and therefore this is gonna run out first, and that's gonna be my limiting reactant. Well, again, we've said that we have to go through the mole ratio, and the reason for that is we have two different compounds over here. You cannot compare the moles of silver nitrate to the moles of potassium iodide. In order to make an accurate comparison, you have to compare the moles of the same compound. So in order to do that, let's go ahead and use the mole ratio. So I have over here the moles of silver nitrate and the moles of potassium iodide that we just figured out, and then we're going to be using these moles and go through the molar ratio to try to figure out which of these two reactants is going to be generating the least amount of moles of the product. So let's do that. We have mole over mole, and we're trying to get rid of the reactant, so that's going to be going at the bottom of the fraction, silver nitrate. And what we want to come out with, which in this case is going to be silver iodide, is going to be going at the top of the fraction. So we want moles of silver iodide, and therefore I'm going to go ahead and write it over here. Now the numbers that you're going to be writing over here should be the coefficients of a balanced reaction. So in this example, we've already said that our reaction or chemical equation is already balanced. So that's going to be 1 over 1. And same thing. Now I'm going to go ahead and do that over here. We want silver iodide, so that's going to be going on the top, but we want moles of that. And we want to get rid of moles of potassium iodide, so that's going to be going at the bottom, and same thing goes in here. We're going to get the coefficients of the balanced reaction. So in this example, silver iodide, there's just 1. Potassium iodide, just 1. Same situation that happened with silver nitrate, just 1 over there. So you don't even have to plug this into your calculator, right? It's just 0.410314 times 1 is going to equal the same thing. And the same thing is happening over here. So technically our answer is going to be the same. But now we have moles of silver iodide, right? We're able to cross out silver nitrate, and we're gonna do the same thing for the bottom. Our silver iodide is going to be our answer. And we're going to get rid of potassium iodide. I forgot to write moles. So now you can go ahead and compare it because you have moles of the same compound. Now you can go ahead and say, well, now that I've done this and I've gone through the molar ratio, I know that silver nitrate is going to be generating the least amount of moles of the product silver iodide. So we know that silver nitrate is going to be our limiting reactant. With this example, since it's a 1-to-1 ratio, you could have kind of stopped over here and say that silver nitrate has less moles than potassium iodide, and therefore silver nitrate is going to be my limiting reactant. But this is not always going to work out. This is only going to work out if you have a 1-to-1 ratio. That's why it's important to go through the molar ratio to try to figure out what the answer is going to be. Again, when we're going from one compound to another compound, you have to go through the molar ratio to get the answer. If you stopped right here and the coefficients would have been something other than 1, that would not have worked out for you. Now that we know what the limiting reactant is, we can go ahead and determine what the theoretical yield is. And the theoretical yield, simply put, is the maximum amount of product that we could possibly produce in a reaction in an ideal world. But we don't live in an ideal world. And some experimental errors are just unavoidable. And on top of that, some reactions simply don't go to completion. And what that means is that some reactants are going to be left over when the reaction reaches an end. So since we know what the limiting reactant is, and we know that the limiting reactant is going to run out first and stop our reaction, therefore limiting the amount of product that we generate, then we can use the limiting reactant to figure out the amount of product that we could possibly make. So we have over here moles of silver iodide that we found through the molar ratio after we figure out the moles of silver nitrate. So again, we found out that the limiting reactant was silver nitrate, so we had used the molar ratio to get the moles of silver iodide, and now we can use these moles of silver iodide to figure out the grams of silver iodide that could be produced in an ideal world, therefore the theoretical yield. So if we have moles and we're trying to go from moles to grams, again, what I want is going to go on the top, and what I want to cross out is going to go at the bottom. The molar mass for silver iodide is going to be 234.77 grams over mole. So looking at this, right, we have grams over mole and grams over mole. So in this example, we don't have to do any type of flipping. We can simply go ahead and multiply it. So I'm going to go ahead and write that down. 234.77 grams over mole. If you multiply that, you can use your calculator. Your final answer is 96.3294 grams of silver iodide. Now, let's not forget our significant figures. We had 3 sig figs starting out with silver nitrate, right? 69.7 has 3 significant figures. So over here, our final answer in our theoretical yield should also have 3 significant figures. So let's stop right here. Do we have to round? No, we don't. So our final answer turns out to be 96, I'm going to write that down, 96.3 grams of silver iodide. So if we lived in an ideal world, this is how much silver iodide we could recover. Since we know the theoretical yield, now we can also find out what the percent yield is. All that we have to do is get the ratio between the actual yield and the theoretical yield and multiply that by 100%. The actual yield is what we actually get when we do the experiment. So say that we go to the lab and we do this reaction right here. And when you're done, you weigh your product and your product comes out to weigh 78.9 grams. If this is what your product weighs and you actually went and you did the experiment, right? This is going to be now our actual yield. So let's take this equation right here and let's plug in our numbers. So this is our actual. So that's going to be 78.9 grams over the theoretical yield, which was 96.3 grams, times 100%, that comes out to be 81.9315%. But let's not forget about our sig figs. We have 3 significant figures here and 3 significant figures here, so our answer should also have 3 significant figures. So we go 1, 2, 3, stop right there. See if we have to round. We do not. So our final answer comes out to be 81.9%. What if I ask you, how much of our excess reactant are we going to have left at the end of the reaction? Well, first off, we know that silver nitrate is going to be our limiting reactant. And therefore, we know that potassium iodide is going to be our excess reactant. And we know that we started out with 69.7 grams of limiting reactant, which equals to 0.410314 moles. And our excess, we started out with 73.0 grams, and that equals to 0.439759 moles. So what we really want to find out here, since we know that silver nitrate is going to be our limiting reactant and is going to be used up first, we want to know how many of these moles of our potassium iodide are going to react with our moles of silver nitrate. And if we're going from one compound to another compound, right, we're going to be using the moles of silver nitrate to try to figure out how many moles of potassium iodide react with them. So we're going from one compound to another compound. What do we have to go through? The molar ratio, right? Every time you start with one compound and you want to end up with another compound, you have to go through the molar ratio. So we're going to go ahead and get started with our moles of our reactant, which are 0.410314 moles of silver nitrate. And we want to come out with moles of potassium iodide. So again, what I want is going to go on the top of the fraction, and what I want to get rid of is going to go at the bottom. So I want moles of potassium iodide, and I want to get rid of moles of silver nitrate. And the numbers that are going to go here are going to be the coefficients of a balanced reaction. So over here we have potassium iodide, it's just going to be 1. We already said ours was balanced, and it's a 1-to-1 ratio, so we have 1 over there as well. And you don't really have to plug this into the calculator, right? It's going to be the exact same. But the key here is that moles of silver nitrate get crossed out, and we come out with moles of potassium iodide. And the answer is going to be 0.410314 moles of potassium iodide react. Okay? So if we know that this amount of moles react, and we started out with this amount of moles, how many moles do we have left over? Think about that for a second. What do you have to do? So if I know that I started out with this, and this amount of moles are going to react, then I'm going to find out the difference. 0.439759 moles of potassium iodide minus 0.410314 moles of potassium iodide. That's going to equal to 0.0 0.294445 moles of potassium iodide that did not react, aka X's. So now that we know that this is the moles that did not react, let's go ahead and find out how many grams then do not react. So we're gonna go from moles to grams. So we have our moles over here, potassium iodide that did not react, and now we're trying to go to grams, right? So from moles to grams, you're going to be using the molar mass. And the molar mass for potassium iodide was 166 grams over mole. So I want grams, that's going to go at the top. I want to get rid of moles, that's going to be going at the bottom. And then over here, you're just gonna write 166.00. You're gonna plug this into your calculator, and the answer is going to be 4.88787 grams of potassium iodide excess reactant. Alright, now let's not forget about significant figures. We started out with 3 sig here, so let's end up with 3 sig as well. 1, 2, 3, stop right here. Evaluate whether or not you have to round in this situation. Yes, because we have a number of 5 or greater, right? 7 is greater than 5. So our final answer there becomes 4.89 grams of the excess reactant. Quick tip, so every time we're going from moles to grams, we'll multiply by the molar mass, and every time that we're going from grams to moles, we divide by the molar mass. So you might ask, well, why don't I just say that? Why do I always say what I want on the top, what I want to get crossed out at the bottom? And the reason for that is, if you're flipping out on a test and you don't remember and you're like, okay, was it multiplying or divided? I don't know. It's easy to go ahead and simply look at the units and make sure that they cross out. If you just look at it and understand it as opposed to memorize it, you're always going to get the right answer. That was it for this video. Thank you guys for watching. I hope you learned something. If you have any questions, feel free to leave me one in the comment section, or you can go ahead and contact your lab instructor for further assistance. Other than that, thank you guys for watching, and I will see you in the next video.